The recent climate summit in Paris set forth an ambitious worldwide goal to prevent global temperatures from rising more than 2 degrees Celsius above pre-industrial times. This will require global greenhouse gas emissions to be cut in half by the year 2040. The success of this effort will require cooperation from all countries and all industrial sectors, including animal agriculture.
So we want to look at the greenhouse gas emissions, in this case, that are coming off the farm, and how we can change strategies and reduce emissions.
If we can become more efficient and reduce the amount of greenhouse gases per unit of product sold, then it's possible that we could hold our emissions steady while at the same time producing more product.
A lot of people think of sustainability as fluff or nice stuff, but I view it as a major business opportunity.
Approximately 43,000 million metric tons of greenhouse gases are emitted from our planet each year as a result of human activity. About 14% of it comes from global agricultural production. This graph shows where the majority of greenhouse gases are coming from and from which human activities. The United States is second only to China as one of the world's top 10 emitters. About 9% of U.S. emissions come from agriculture. These emissions come directly from several sources: agricultural soils, enteric fermentation from ruminant animals, manure, as well as some from rice cultivation and field burning of agricultural residue. These agricultural emissions include not only carbon dioxide, but also methane and nitrous oxide, which can be represented in carbon dioxide equivalents. Nitrous oxide comes primarily from the nitrogen cycle in agricultural soils. Methane comes primarily from either enteric fermentation or the anaerobic decomposition of manure. On the dairy farm, most greenhouse gas comes from feed production, enteric fermentation, and manure. In pork production, manure and feed contribute nearly equally to emissions. The main contributors in beef production are somewhat different. Feed production, cow-calf operation, and feedlots are the main target areas. Emissions from the cow-calf phase of production are primarily methane from enteric fermentation. Emissions from the feedlot are primarily enteric methane and nitrous oxide from manure. Looking at on-farm poultry emissions, 70% come from feed production, about 16% from manure, and 14% from on-farm energy use. The reduction of greenhouse gases is known as mitigation because it refers to mitigating future changes in climate. As we begin to discuss the many ways to mitigate greenhouse gas emissions from agriculture, we first consider the arguments for and against mitigation. Arguments against mitigation include: because agricultural emissions are generated in the production of a critical product, food, some argue this makes the industry exempt from any national or global emission reduction strategies. Some believe the cost of reducing emissions would outweigh any potential benefits to the environment. And others suggest the relative amount of emissions coming from U.S. agriculture on a global scale is so small that reductions would have no real impact on the world total. However, other voices in the agricultural industry arguing for mitigation explain that mitigation can work well economically for farmers, or is simply just the right thing to do.
There's several reasons why they'd want to reduce emissions, and one of the most important is to reduce their cost or improve their efficiencies. You know, if they're able to, through diet manipulation, for example, improve the productivity of their animals, and also reduce emissions, then they're all for it.
In our farm, on a mass balance basis, I calculated that we have $800,000 a year in resources in our control that we waste. That's a lot. So we're systematically trying to recover those resources, sand, carbon, nitrogen, phosphorus, harvesting them and adding to the business revenue and reducing losses and risks. So to me, it's a substantial business opportunity we must pursue. Coincidentally, it's good stewardship.
I think every farmer should have an interest in this, and the reason why I think that way is because improving your environmental performance often or most times goes hand in hand with improving your pocketbook. Because these efficiencies we are talking about that reduce environmental footprint are the same efficiencies that increase your pocketbook.
A farm product's environmental footprint or carbon footprint is also known as its emission intensity. Emission intensity refers to the amount of greenhouse gas emitted per unit of production. Emission intensities can vary dramatically in animal production. This suggests there is great potential to reduce or mitigate greenhouse gas emissions. When assessing the emission intensity data of a given product, it's important to know what was included in the assessment. Did the assessment look at only direct farm emissions, or did it include indirect emissions or emissions that occurred after the product left the farm? Over time, animal production has become more efficient through improvements in technologies. This increase in efficiency has also led to reductions in greenhouse gas emission intensities. Several studies show this. One study shows the emission intensity of beef in the United States decreased by 17% from 1977 to 2007. Another study of milk's emission intensity showed a 63% reduction in emission intensities between 1944 and 2007. Recent life cycle analyses show that emission intensities for a product can vary significantly among different geographic regions, among different species of animals, within a species, and among different countries. One example can be seen in Dr. Greg Thoma's life cycle analysis of swine emission intensity. The study showed emission intensity varied from one geographic region to another due to differences in temperature, as well as feeding and manure management practices. Region 4 had the highest emission intensity. First, because it has warmer average temperatures than regions 5 and 7, and second, because states in Region 4 have more manure systems with anaerobic lagoons. The highest emission intensity in Region 4 is twice as high as the lowest emission intensity in Region 5. Similar examples of geographical emission intensity variation can be found in other agricultural sectors. This suggests that within any industry, there is the potential to economically reduce emissions.
The fundamental conclusion at the end of the study was the most important thing is the way that an individual farm is managed. Our conclusion from that was that it's not what you're managing, but how you're managing it. And so the implementation of best or beneficial management practices and care of the animals, care in the ration formulation, all of these things contribute to the better performing farms.
Emission intensities also vary by species. A study by the Food and Agricultural Organization looked at the emission intensities of livestock production on the basis of kilograms of CO2 equivalents per kilogram of protein produced. There were obvious differences among species. Average emissions per unit of protein ranged from 40 to 342 and were lowest in poultry and highest in ruminant animals. More importantly, however, the data shows the variability of emissions within a species. Globally, emissions from beef production vary the most. 90% of beef emissions range from 100 kilograms of CO2 equivalents per kilogram of protein all the way up to 500 kilograms of CO2 equivalents per kilogram of protein. These variations in emissions reflect a variety of factors, including genetics, nutrition, climate, and farm management. Globally, there is even wider disparity in greenhouse gas emissions among different regions of the world. This suggests that the real potential for reducing emissions from agriculture may come from global efforts. The same FAO study highlighted dramatic differences in emission intensities per country, with beef ranging from about 15 to 75 kilograms of CO2 equivalents per 100 kilograms of live weight. Average dairy emission intensities from milk ranged from about 1.5 to 9 kilograms of CO2 equivalents per kilogram of milk produced. After looking at the wide range of emission intensities in different farming systems, it's clear there is potential to reduce emissions with strategies that are economically viable for farmers. LCA studies can pinpoint specific areas to target with emission reductions. We will look at several areas of focus where there are opportunities for mitigation: agricultural soils, enteric fermentation, manure management, farm energy, and production efficiency. Many of the mitigation methods we will be discussing have been reviewed and analyzed in online publications, such as the Journal of Animal Science and Global Change Biology, and are supported by a large number of worldwide studies and assessments. Greenhouse gas emissions from agricultural soils used in feed production is a large contributor in all animal and poultry products. Emissions are primarily nitrous oxide, which is emitted from both cropland and pastures. Nitrous oxide is generated in industrial processes as well as naturally in the environment. In soils, nitrous oxide is formed during the phase of the nitrogen cycle where there is cycling of aerobic and anaerobic conditions. Higher nitrous oxide emissions come from soils that are warmer, wetter, or have higher soil nitrogen concentrations.
Generally, the more moist the soil and the warmer the soil, the more nitrous oxide emission. In general, climate change is working against us environmentally, so there's all the more need to mitigate and put in mitigation practices in to compensate and maintain more sustainable systems.
Farmers can reduce nitrous oxide emissions by using best management practices for fertilizer and manure. These practices include the proper application rate, timing, and placement of commercial or manure nitrogen on the soils. These practices are widely known, and they can save farmers money on fertilizer costs. Tillage is also a factor in reducing emissions. This study looking at corn production compares different combinations of tillage and nitrogen fertilizer rates. In these scenarios, emissions ranged from a high of 167 grams of CO2 equivalents per kilogram of grain to a scenario where 89 grams of CO2 equivalents per kilogram of grain were actually captured in the soil. Key to reducing emissions was proper application rates, replacing commercial fertilizer with manure, and reducing tillage. Other methods for reducing emissions include winter cover crops and incorporating perennials. The success of any of these methods depends on geographic region, soil type, temperatures, and other factors. Current research is also looking at how rangeland and pasture can sequester or capture carbon. This is sometimes referred to as carbon farming. The research is looking at how carbon farming will impact different types of grasses and forages, as well as grazing scenarios and fertilization. In the beef and dairy industry, methane from enteric fermentation is the biggest source of greenhouse gas emissions. Enteric fermentation occurs in ruminant animals and refers to the microbial breakdown of fibrous plant material, or cellulose, into energy and nutrients. Methane is a byproduct of this fermentation process and is exhaled or belched from the animal. Methods to reduce enteric methane include dietary changes, such as feeding higher quality and more digestible forages or a higher percentage of grain. A recent review article on enteric fermentation in dairy concludes that such feeding and nutrition practices may reduce methane emissions by as much as 2.5 to 15%. However, this review also concluded that the biggest reductions in enteric fermentation are related to gains in efficiency per unit of production. For instance, a healthy animal will produce more product than an unhealthy animal, but will emit similar amounts of enteric methane. Nitrous oxide and methane are emitted from manure from the time it leaves the animal until it is taken up by the crops. This chain of events, from diet and housing to storage to treatment to spreading, is referred to as the manure management system. Each phase interacts with subsequent phases in the system. For instance, the animal's diet affects the nutrient content of the excreted manure. Less manure or fewer nutrients in the manure will reduce the emissions from each part of the manure management system. Therefore, emission reductions from manure management must be evaluated as a whole system rather than by individual components. Before diving into the details about mitigating emissions from manure, it's important to understand the science of how methane and nitrous oxide are generated. The formation of these gases requires a few things: a proper substrate composed of nitrogen, carbon, and other nutrients, and the right environmental conditions, including temperature, oxygen concentration, and moisture content. Lastly, time is needed for the gases to form. Aerobic conditions, where there is oxygen, are found in dry manure. Anaerobic conditions, where there is no oxygen, are found in slurry or liquid manure. Methane is formed in anaerobic conditions, while nitrous oxide requires a cycle between anaerobic and aerobic conditions. Mitigating emissions from any point in the manure chain requires some manipulation of these factors or taking steps to prevent gases from being emitted, for instance, using covers. With these factors in mind, we can look at the different stages in manure management and see how any changes might affect emissions. Mitigation methods for manure emissions begin with the animal's diet and housing. Changing to diets that are more digestible or that most closely match the needs of the animal in all phases of production and in all seasons of the year will result in less manure produced and fewer nutrients in the manure. This limits the formation of greenhouse gases throughout the manure system.
Dairy farms that manage their feed well, they will reduce both the enteric emissions from the cow, and they will also reduce the methane emissions from the waste because the cow is using the food more efficiently, so there's less volatile solids going into the waste to produce less methane. In addition to the fact that dairy farmers that manage the nitrogen in the diet are also better managing the nitrogen, that you're reducing the amount of nitrogen that could come off as nitrous oxide, which is a 300 or 298 times more potent greenhouse gas than CO2.
Other ways to mitigate manure emissions focus on the animal's housing and manure collection system, which also affect greenhouse gas formation. Techniques to reduce emissions from animal housing and manure collection include the following: moving the manure from the barn to the storage area sooner, which will lower barn emissions. Keeping feedlots dry, since wet feedlots generate more methane emissions. In poultry barns, adequate litter will result in drier conditions. This limits both methane and nitrous oxide formation. It is also important to focus mitigation efforts on manure storage, which is typically the source of most of the emissions. This is primarily because of the amount of time the manure is kept in the storage. Techniques to mitigate greenhouse gas emissions from manure storage include shorter manure storage times. A daily haul or monthly hauling allows less time for the gases to form. Smaller manure storage surface areas will also reduce emissions as the manure has less contact with the atmosphere. Cooler manure temperatures will reduce formation and emissions of both nitrous oxide and methane. Creating these conditions artificially is not economical, but animal agriculture in cooler climates has this advantage. Using covers. Organic or permeable covers, such as crusts or straw covers, unfortunately can actually enhance nitrous oxide formation because the covers allow for the cycling of aerobic and anaerobic conditions. However, using impermeable covers on manure storage will reduce nitrous oxide formation and will capture any methane produced.
In looking on how to mitigate these emissions, what's great about methane is it's combustible. And when you combust it, it turns into carbon dioxide. So you just drop that 34 factorial down to 1. Right now, when you have an open lagoon, it's emitting the methane. You put a little cap on it, it bubbles up, it collects the methane goes out, it flares, it destroys. You've now just mitigated that emission factor. If a farm is interested in mitigating their greenhouse gases, putting a simple cover, we're not talking an anaerobic digester, we're not generating electricity, we're just covering, we're capturing, and we're flaring the methane from the liquid portion. It's within the range of the social costs, and it's within the range of current markets that one might consider doing it. In addition to the fact that covers, they reduce your hauling costs, it reduces the rainwater, which also increases your storage capacity, right? You can now grow your farm or store longer. It addresses odor, and it also addresses extreme rain event overflows.
Manure treatment systems can also be used to reduce emissions. Separating the liquids from the solids will reduce the substrate in the liquid part of the manure. This can reduce gas formation in both the manure storage and in land application of the liquid portion of the manure. Aeration of the manure will limit methane formation, but intermittent aeration could result in more nitrous oxide emissions. Some farms in Europe are reducing emissions by adding chemicals to lower the pH of the manure to below 6. This inhibits microbial activity and reduces methane emissions. Anaerobic lagoons are designed to decompose the manure, but the result is increased methane formation. Covering these lagoons will trap any methane. Engineered anaerobic digesters convert manure and other organic wastes into energy. A digester produces methane from manure. The methane is then captured and used to generate heat and electricity. This anaerobic manure digester at the Vanderhoek Dairy Farm in Washington State takes in about 50,000 gallons of manure and food waste combined per day.
All the manure comes in, piped over from our other dairy, goes into a collection pit underneath the cows, and from there it gets pumped into the digester, which is back here. Once the material goes into the digester, we heat it up. It flows through the system for the 20 days. The bacteria produce methane gas, which floats to the top, and then comes out of the digester, flows through a pipe into the building, and produces electricity. So after the manure comes out of the digester, it's piped over to a manure separator. From there, the solids go off one side, the liquid goes into the lagoon to be applied to the fields at a later time as a fertilizer for the grass and corn.
We take the natural bacteria that's going to occur anyways in the lagoon, and we put it into an engineered system, into an enclosed vessel, mix it the way we want, give it the exact temperature that we want to optimize the process.
A digester like this one can reduce the farm's greenhouse gas emissions by about 3 to 4 metric tons of CO2 equivalents per cow per year.
We'll make methane, but instead of the methane being released into the air, we collect it, put it through an engine, get energy out of it, and in the process of getting energy, convert it to CO2, which is still a greenhouse gas, but it's a greenhouse gas that's 25 times less powerful. So you've really improved the climate footprint for the dairy.
Finally, there are techniques for mitigating emissions from the land application or spreading of manure. Greenhouse gas emissions from land application are minimized if manure is applied onto dry soils. Emissions are reduced when manure is applied to soils with a higher amount of organic material. Land application of solid manure is typically not a source of greenhouse gas emissions. Liquid manure that is incorporated or injected into the soil rather than applied to the surface may result in lower methane emissions, but depending on soil type and soil moisture, it could increase nitrous oxide emissions. Overall, greenhouse gas emissions from manure spreading are the end result of what's happened along the entire manure management system, including the animal's diet and housing, and the collection, storage, and treatment of the manure. Some greenhouse gas emissions also come from farm energy. Farms use energy for ventilation, heating, lighting, and running tractors and other equipment. In beef operations, on-farm energy use contributes a relatively small percentage of overall greenhouse gas emissions. The same goes for dairy and swine, where farm energy use represents only about 4 or 5% of emissions. In poultry operations, emissions from farm energy use are somewhat higher, contributing about 14% of poultry emissions. Reducing greenhouse gas emissions from farm energy use can happen in two ways: using low-carbon energy sources, such as biofuels or renewable electricity, or using less energy on the farm. Strategies may include high-efficiency lighting, ventilation, and heating and cooling systems that are properly designed, operated, and managed, proper insulation and sealing of leaks, and efficient motors and motor controls. Reducing energy use on the farm can be cost-effective. Converting to higher efficiency equipment saves on energy costs, resulting in short payback periods. Turkey farmers in Minnesota who switched to LED lighting systems in their buildings are seeing paybacks on their investment in 3 years or less, thanks to the savings on energy costs. Energy economic assistance programs through local, state, and federal governments or through utilities can help offset the costs of this energy-efficient equipment. Often, the most impactful strategies for reducing emissions from animal agriculture focus on improving production efficiency. In general, this means producing more milk, meat, or eggs with the same or fewer inputs. This gets back to reducing emission intensity.
The higher the production per animal, the less nutrients that are used for maintaining that animal, the more the nutrients go into the production of milk, basically. So overall, you're getting more milk with, say, equal or less emissions, and that's going to benefit your overall footprint.
If we look at agriculture over the past century and a half, we see the gains made in yields per acre, output per animal, and in animal feed conversion efficiency. For example, looking at yields per acre, average corn grain yields in 1940 were about 25 bushels per acre. Compare that with yields today of more than 160 bushels per acre. These increases in efficiency came with the use of fertilizer, improvements in plant genetics, irrigation, and other factors. Looking at increases in output per animal, the dairy industry in the United States gives us one example. Milk production per cow in the U.S. rose by 16% over a 10-year period, from 2001 to 2010. This is an increase in production efficiency at a rate of 1.6% per year.
The average cow here in the United States produces approximately 20,000 pounds of milk per year. The average cow in Mexico produces approximately 4,000 pounds of milk per year. So it takes 5 cows in Mexico to produce the same amount of milk as 1 cow here. If you go further internationally, in India it takes 20 cows to produce the same amount of milk as 1 cow here. So what this really means is that we have learned to intensify, on the one hand, agricultural production, but this intensification came with leaps in efficiency.
Improved feed conversion efficiency is typically a good indicator of reduced emission intensity. Feed conversion efficiency in meat animals is simply the amount of feed nutrients required divided by the live weight of the animals produced. In dairy, it is the amount of feed nutrients required divided by the amount of milk produced. In the broiler chicken industry, we can see improvements in feed conversion efficiency since 1940. Back then, a chicken required 4 kilograms of feed for every kilogram of gain in live weight. Today, it takes half that amount of feed, or 2 kilograms, for the same animal growth. A variety of factors contribute to feed conversion efficiency. Improvements in animals' health and environment. Improvements in nutrition and feed delivery. Genetic selection for geographic regions. Reductions in heat stress. Reductions in disease. Improved fertility and reproduction. All of these factors are common goals for all farmers, and all are important when trying to improve feed conversion efficiency and reduce emission intensity. Not all of them are that easy to implement, which is why there is variability among farmers in terms of emission intensity. Feed conversion efficiency varies widely within species, indicating good opportunities to reduce emissions. In the swine industry, the most efficient producers, the top 10% with conventional finishing systems, have a feed conversion of 2.34. This is in contrast to the lowest 25% group. Those producers have a feed conversion of 2.98. This is a 21% reduction from the worst 25% to the top 10% of producers. This 21% reduction in feed conversion efficiency would translate into a similar reduction in greenhouse gas emission intensities from swine. This same variability can be seen between farms in other species, and as we saw, the variability gets much greater as we look at global agricultural production. There are many opportunities to reduce greenhouse gas emissions from animal agriculture. In this video, we've described strategies to mitigate emissions in the areas of agricultural soils, enteric fermentation, manure management, energy use, and production efficiency. The most significant opportunities to reduce emissions are in manure management and in improving production efficiency. Wider use of these strategies and cooperation throughout the industry are important. Farmers in every country can play a significant part in reaching that 2040 goal of cutting global emissions in half, while at the same time producing more food more efficiently for the entire planet.